Hello students, welcome to the 13th lecture on particle physics. And yesterday we were discussing about these symmetries and their role in physics. Today I am going to talk about discrete symmetries, and in this we shall discuss about the parity, charge conjugation, time reversal, CP, and finally we shall talk about CPT. Now, when we talk about parity, then it's defined as an operation of spatial inversion, and it takes r to minus r while keeping time t unchanged. And since r changes to minus r, therefore the momentum of the particle mdr by dt, if this changes to minus p, and p and r both change sign, and therefore the angular momentum, which is defined as r cross p, this does not change sign, and j, which is sum of orbital and spin angular momentum, that also does not change sign under parity. And therefore we have quantities which change sign under parity and the vector quantities which do not change sign under parity. Those quantities which change sign under parity, vector quantities, they are called pure vectors or polar vectors or simply vectors, while these quantities which do not change sign but transform in the same way under proper Lorentz transformation as a polar vectors do, these quantities are called axial vectors or pseudo vectors. And parity is a space-time symmetry performed by the discrete transformations, while the continuous transformations we have discussed yesterday, that was infinitesimal summation of the transformation. You sum the infinitesimal transformations in the case of continuous symmetry, while here in the case of discrete symmetry, you have the discrete transformations. Now, the other one is charge conjugation operation. What does it do? It takes a particle to an anti-particle state. That means if I talk about charge conjugation operation operating on a pi plus state, it gives me a pi minus. And it is an internal symmetry, and the different quantities that it changes are the charge, because we are taking from pi plus to pi minus, proton to anti-proton, and therefore charge is getting changed. Baryon, because proton is becoming anti-proton, therefore baryon number is getting changed. Electron is becoming positron, lepton number is getting changed. Magnetic moment is getting changed because the sign of the charge is getting changed. Strangeness, when I'm doing it, the operation on sigma plus, it is becoming sigma plus bar. And the baryon number of sigma plus bar is -1, and its strangeness is +1. And then the third component of isospin, because the charge sigma plus is becoming sigma plus bar and sigma minus is becoming sigma minus bar. Then the quantities which do not change sign under C, they are linear momentum, angular momentum, isospin, magnitude of the magnetic moment, etc. And we will discuss in detail about it. Then we have the third discrete operation that we will discuss is the time reversal, and is a again is a space-time symmetry performed by the discrete transformation. Suppose I have got a ball and I am dropping it from a height h and I am making a movie of that. Now, as the ball will come closer to the ground, it will gradually increase its kinetic energy and ultimately it will hit the ground. Now, with the same kinetic energy as with which it has hit the ground, if I impart this to this particle, then the particle will go back to its original point A. Therefore, the it if we have some process that is taking place in the forward direction t, in the reverse time, if I am getting the same point, then we say that the process is invariant, otherwise it changes. Now, the Hamiltonian of the system, if it commutes with the parity operator or charge conjugation operator or time reversal operator, then the quantum number associated with the parity operator or charge conjugation operator or time reversal operator, that is a good quantum number. Now, in the case of strong interactions as well as electromagnetic interaction, parity, charge conjugation operation and the time reversal operation, they commute. These operators commute and therefore quantum number associated with these operators are conserved quantum number. While Hamiltonian for the weak interaction does not commute with the parity operator or charge conjugation operator or time reversal operator, and therefore we say that in the weak interaction parity is violated, etc. Therefore, we shall discuss about them in greater detail later. Therefore, we are going to start with parity, and basic question that one may ask: do the laws governing a physical phenomena hold when the phenomena is observed in a mirror? If the answer is yes, then we say that the law is invariant under mirror reflection. For example, if we are dropping a ball of mass m from a height h, under the action of gravity, the law governing its motion will be given by, say, I'm talking about a ball being dropped and this is my z direction. This is how the ball is getting dropped. Then the equation of motion is given by md square z by dt square is equal to minus mg. Now, what will be the mirror reflection of that? Say this is the mirror. Z will change to Z prime, the other things will remain invariant, and therefore we will say that the law remains invariant in this case under mirror symmetry, and therefore this law is invariant under mirror reflection. Now let us come to the parity transformation. In this transformation, all space components, that is x, y and z, they change to minus x, minus y and minus z. Because mirror symmetry, when we talk about that, it is two-dimensional thing. Here we are talking about the three-dimension where we have, that is why we have written r changes to minus r. If a law governing a physical phenomena is found to be invariant under this transformation, the phenomena is said to obey the law of conservation of parity. Now let us see that how electric field behaves under parity operation, or magnetic field behaves under parity operation, or Maxwell's equations behave under parity operation. Now consider, for example, a particle with charge q moving in a uniform electric field E. The force on the particle will be QE, and the motion of the particle will be described by md square r by dt square, that is equal to QE. Now let us do the parity operation and to see first how E transforms under parity operation. Now, the electric field due to charge Q at point R is given by E is equal to 1 by 4 pi epsilon naught Q by R cube times R. Now, when we are talking about R2 minus R, there will be nothing that will happen with Q. Nothing will happen with the denominator because it is mod. Therefore, E will change to minus E. Now, notice in the previous case, we had md square r by dt square is equal to QE. Now, when we are operating by the parity operator, E changes to minus E, and that is why the equation of motion remains unchanged when you change R to minus R. Therefore, the electrostatic force is invariant under the parity operation. Now, similarly, if we want to talk about how magnetic field behaves under parity operation and what happens to the equation of motion, consider a charged particle moving in the magnetic field, then the force acting on the charged particle is given by QV cross B. And therefore, equation of motion will be md square r by dt square, that will be q dr by dt cross B. Now, we have to first see how B transforms under the parity operation. And for this, we have to go back to the class 12th and recall the Boyd-Sever law, where we consider that there is a wire and through which a current I is flowing, and we are taking a small element dl and want to calculate the magnetic field at a point P. Then if you recall the Boyd-Sever law, this is mu naught by 4 pi I dl cross r by r cube. Now, when we operate parity operation, then I is dq by dt, nothing is going to happen there. Denominator is not going to change, mu naught is a constant. Then under parity, r will change to minus r and dl will change to minus dl. Okay, this is also the element that we are talking about. Under parity operation, it will change sign and r will change sign, such that the magnetic field is not going to change sign. And that is why when you notice here, dl is changing sign, dr is changing sign, and magnetic field is not changing sign. Now, that means electric field changes sign under parity operation, while magnetic field does not change sign under parity operation. Now, look at the Gauss's law in electrostatics, where divergence of E is rho upon epsilon naught, is the charge density. Therefore, this is not going to change under parity operation. While what is del? I delta by delta x plus j delta by delta y plus k delta by delta z. X, y, z, they change sign under parity operation. Therefore, del changes sign under parity operation. And we have change in sign in E, change in sign in del. Overall, there is no change in the expression of the Gauss's law in electrostatics. Similarly, if we talk about Faraday's law, then E changes sign under parity, del changes sign under parity, while B and T, they do not change sign under parity. Therefore, again, this is invariant under parity operation. Similarly, you can simply check it by looking at the Ampere's law, where del is changing sign, B is not changing sign, J is changing sign, and here E is changing sign. So therefore, overall, there is a change of sign on the left hand side as well as on the right hand side. Therefore, there is no change of sign, and what we are realizing that Maxwell's equations are invariant under parity operation. Now, the alternative way of writing electric field and magnetic field are also in terms of the scalar and vector potentials. And we can see that how does this phi and phi A transform under parity operation. Recall, B is del cross A. B is not changing sign. Del is changing sign, and therefore A has to change sign. Therefore, A changes to minus A under parity operation. On this side, E is changing sign. Then we have phi minus del A by delta T. A is changing sign. Phi is there, is changing sign. Therefore, under parity operation, then what will happen to E will change to minus E, del will change to minus del, and phi will change to minus phi. Therefore, in principle, A is changing to minus A and del is changing to minus del to keep the magnetic field unchanged. Now, using this concept that the vector potential changes sign under parity operation, we can determine the parity of photon. And now the examples which we are taking, they are really important in the understanding of the properties of the particles, as well as these are often asked in the different competitive examinations. For example, if we want to determine the parity of photons, then what we know that a photon propagating freely in a space with momentum k is described by a wave function that is given by n times epsilon times e to power minus, either you can write it as minus I k dot r, 4 vectors, or you can write it as minus I et minus k dot r. Therefore, this E is the energy of the particle. Don't get confused with the electric field. This is the energy of the particle. And we are taking exponential of some quantity. And we know that we can only take exponential of numbers. And therefore, under parity operation, this should be a scalar. And that is why nothing will happen to this part. N is the normalization constant, and that means if A is changing to minus A, that means the polarization vector of the photon is changing sign under parity operation. Therefore, if under parity A is changing to minus A, epsilon is changing to minus epsilon. Okay, and this implies that the parity of photon is odd. The quantities which transform, as we have discussed in the beginning, but for the completeness, the quantities which transform as vectors under Lorentz transformation, as well as change sign under parity, are known as polar vectors or simply vectors or pure vectors, whereas the quantities that transform as a vector but do not change sign under parity operation, they are known as pseudo vectors, or the other name of this is axial vectors. Similarly, the quantities which transform as scalars but do not change sign under parity are pure scalars. That means if you talk about the Lorentz transformation, T prime is T minus Vx by C square upon square root 1 minus V square by. Under this Lorentz transformation, if a quantity is unchanged as well as it is unchanged under the parity operation, then we say that quantity is a pure scalar or simply a scalar. But if it transforms in the same way what a scalar does, that means it remains invariant under proper Lorentz transformation, but changes sign under parity, then that we call it as pure, pseudo scalars. Therefore, we have to understand the difference. We have vectors, pseudo vectors, we have scalars and pseudo scalars. When we talk about a parity of a particle or a system, there could be intrinsic parity or there could be orbital parity of this. And we have to understand the difference between intrinsic parity and orbital parity. First, let us take the example of intrinsic parity. Now, consider a particle moving with momentum p its momentum eigenfunction is given by this expression. Again, this is minus I k dot r sort of thing. Now, under parity operation, suppose we operate by parity operator, we have eta as the eigenvalue, psi p, and this r will change to minus rt. Equivalently, we can write it as p changing to minus prt, and therefore such that if the particle is at rest, that means its momentum is zero, psi prt is an eigenstate of the parity operator with the eigenvalue eta. And this is known as the intrinsic parity of the particle. Therefore, the intrinsic parity corresponds to the parity possessed by a particle when it is absolutely at absolute rest. Now, parity quantum number presented by such particles is known as the intrinsic parity, which is nothing but the parity presented by the particle at rest. Now, if you again apply the parity operation, for example, this psi prt, once you have eta psi minus prt, you repeat the operation, then you will get eta squared psi prt. Psi prt is the original state that we were talking about. If you compare the extreme left and extreme right hand side, then eta square should be 1, and then that means eta can be plus 1 or minus 1. If eta is plus 1, then that is known as even parity state, and if eta is minus 1, then that is known as odd parity state. Now let us take a few examples. Now if we, for example, we have sine function and we operate by parity operation, then sine of minus theta is minus sine theta, and that means here this is minus psi. Therefore, the wave function of the type of sine theta, the parity eigenvalue is minus 1, odd parity. But instead of that, if we take cosine theta, then cos of minus theta is the same as cos theta, and therefore the eigenvalue will be plus 1, and that means this will have even parity. But if we take a combination of them, sine theta plus cosine theta, then we say that psi is not a definite parity state, because sine theta is changing sign, cos theta is unchanged. Therefore, we are getting a new wave function, cos theta minus sine theta. Now, in the case of atoms bound by the central potential, VR, what are the central potential? For example, if I am talking about the Coulombic potential, Q1, Q2 by R. If I am talking about some exponential potential, where R0 is a constant which has got the dimension of the distance, because we have to take the exponential of a scalar quantity. If R is the distance, which is generally in meters or centimeters or Fermi or angstrom, then we have to add a quantity here, and that quantity here I am calling it by the name R0, where R0 has the same dimension as that of R, but it is a constant quantity. R is going to vary, R0 is not. R0 is not going to vary, it is a constant, and therefore this is an example of exponential potential. Similarly, we can take an example of Gaussian potential, alpha. Simply in literature you will find from minus alpha r square. Similarly, you can talk about Yukawa potential, Halton potential. These are all central potential. That means the potential depends upon the absolute distance between the two particles. Therefore, if we are talking about potentials which depend upon the absolute distance between the particles, then in that case, the system that we are talking about, the atomic state, has a definite parity. Now, let us try to understand the meaning of orbital parity. The wave function for the atomic states is defined as the product of radial wave function r and angular wave function, which is generally written in terms of spherical harmonics, and therefore we have the psi r theta phi in spherical polar coordinates, we are writing it as RR YLM theta phi. This is given in every quantum mechanics book. For example, you may look at Schiff, or you may look at Resnick and Iceberg, or any fundamental book on quantum mechanics. And then this YLM theta phi we write in terms of associated Legendre polynomial and e power I m phi. Now, what is happening here? R is changing to minus R under parity operation without changing the magnitude of R. R under parity operation, R changes to minus R without changing the magnitude of R, and therefore here what is happening, you have R here, parity operation is giving you minus R, and that is equivalent to changing, since this magnitude is not being changed, theta is changing to pi minus theta and phi is changing to pi plus phi. This is what I have demonstrated here, that if we have x, y and z coordinates and we talk about the zenith angle and the polar angle, zenith angle is theta and polar angle is phi, then for a point here, say P, we are defining these vector R, then when we operate it by a parity operator, then we are getting minus R. That minus R equivalently we can get by keeping R unchanged while changing theta by pi minus theta and phi by pi plus phi. And this is I am going to exploit in this expression. Look at it. Psi r theta was RR. Since capital R is a function of the absolute distance or simply the R scalar, and then we have this fellow which are constant, then we have PLM cosine theta e to power im phi. And mind it, what we are doing, we are changing theta to pi minus theta and phi to pi plus phi to get R to minus R. Therefore, we have PLM cos pi minus theta, and this is equivalent to minus 1 to the power L plus M PLM cosine theta, while P e to power im phi, when we are changing to e to power im pi plus phi, then this is e to power im pi times e to power im phi, and this is cos m pi plus I sin m pi, and e to power im phi. Take the different values of m, 0, 1, 2, 3. You will find that you can write it in terms of minus 1 to the power m, because this will be, for m equal to, this will be 1, this will be 0. And then when m is equal to 1, this is minus 1, this is 0. When it is 2, this is 0 and this is plus 1. Therefore, alternatively, it is changing sign, and that is why I am writing it as minus 1 to the power m e to power im phi. Therefore, we had PLM cosine theta I times, we had in that expression PLM cosine theta times e to power im phi, which is equivalent to minus 1 to the power L plus twice m PLM cosine theta e to power im phi. And since this is minus 1 to the power twice m, no matter what value of m you have, this is always, this will give you plus 1. Therefore, this is equivalent to the complete expression of psi r theta phi with a factor of minus 1 to the power L. Therefore, for atomic system or for a composite object, we define parity also in terms of orbital parity. Therefore, we have intrinsic parity of the particle as well as we have the orbital parity of the particle. And we can determine the parity of the different particles using this method. And we shall, for example, if we talk about the atomic states in S state or D state or higher states, then S corresponds to L equal to 0, D corresponds to L equal to 2, and so on, while P corresponds to L equal to 1 and F corresponds to L equal to 3. Therefore, for SD etc. states, this will be even parity state, while PF states, this will be odd parity state. And this we will use in the determination of the intrinsic parity of the particles that we will talk about in the next lecture. Thank you very much.